Hi and welcome to part 5 of this video playlist about the preparation of pyridines. This video is about the arylation of pyridines by substitution of hydrogen. This will cover oxidative pyridine dimerizations and the rather unique ability of pyridines to arylate electron-rich arenes. I'll also show you some strategies similar to those discussed in the video about alkylations. One arylation strategy is the addition of polar or transition metal organometallics to pyridines. This initially yields a dihydropyridine, which can eliminate the metal hydride upon heating or may require an additional oxidant to achieve aromatization. If a given arene is not nucleophilic enough, activation of the pyridine with an acid or by transient alkylation at nitrogen can help. A further strategy is the addition of aryl radicals to pyridines, metallated pyridines or pyridinium salts, followed by oxidation. Aryl radicals can be generated from aryl halides by homolytic halide abstraction or by single electron transfer to an arene, for instance with sodium. I'll show you now some specific examples of each of these arylation strategies, beginning with pyridine dimerizations. The herbicides paraquat and diquat are such dimers, and 2,2'-dipyridyl is an important ligand for transition metal complexes. When pyridine is heated with Raney-nickel at the air, this dimer is slowly formed with high regioselectivity. Dimerization probably proceeded by addition of a 2-pyridyl radical to an organonickel intermediate. Another isomer can be prepared from pyridine and sodium in a mixture of liquid ammonia and DMF, again in the presence of air. This dimerization proceeded already at low temperature and was faster than the nickel-catalyzed dimerization. Instead of oxygen, also sulfur dioxide can be used to dimerize pyridyl sodium intermediates. Despite the high acidity of 2-picoline, still a substantial yield of dimer was obtained. Here, the initial reaction with sodium was conducted in refluxing dioxane. N-acetylpyridinium salts are more easy to reduce to radicals than unactivated pyridines. In this example, the dimer of a dihydropyridine was prepared by treatment of pyridine with zinc and an excess of acetic anhydride. Dehydrogenation with palladium on charcoal and hydrolysis gave the dimerized pyridine. In this example, a pyridyl radical was generated by oxidation with nitrobenzene of a cuprate of 2-chloropyridine. Mainly one isomer of the dimerized pyridine resulted. This reaction may be a bit confusing at first sight. No matter if 2 or 3-bromopyridine was treated with the radical starter AIBN and a large excess of pyridine, the same unsymmetric pyridine dimer was obtained. The reason for this probably was that 2-pyridyl radicals are electrophilic and will add to pyridine at position 3, while 3-pyridyl radicals are more nucleophilic and add to pyridine at position 2. The excess AIBN was required to oxidize the intermediate dihydropyridyl radicals to the final product. Strangely, the authors also added a reducing agent, which was, however, not really required here. Aryl radicals can also be generated by oxidation of aryl hydrocenes, as in this example. When doing so in a large excess of pyridine, arylated pyridines can result. In this example, the regioselectivity of pyridine arylation was low, however. Also, aromatic boronic acids can serve as radical precursors, as shown here. A combination of persulfate and silver nitrate was used as oxidant, but again the regioselectivity was low. I'll show you now some examples of electrophilic aromatic substitutions with pyridinium cations as electrophiles. In this example, a substituted isoindole was prepared from isoindolinone, pyridine and benzoyl chloride. This reaction probably proceeded by initial activation of both pyridine and isoindolinone by benzoyl chloride. Interestingly though, benzoylation of isoindolinone at oxygen would generate a highly reactive nucleophilic isoindole, while acylation of pyridine at nitrogen yields an electrophilic pyridinium salt. Dihydropyridines are powerful hydride donors, and hydride migration in the first dihydropyridine intermediate would cause reduction of the carbonyl group and formation of a new isoindole, which could react once more with N-benzoyl pyridinium chloride. Similar to the previous example is the activation of pyridine with cyanuric chloride followed by coupling with an aniline. The reaction also required aluminum chloride, probably to capture the hydride released during the aromatization of the intermediate dihydropyridine. Both alkyl and aryl lithium compounds usually add to pyridines to yield dihydropyridines. If these are heated before hydrolysis, a substituted pyridine can be obtained directly by elimination of lithium hydride without any additional dehydrogenation step. In this example, pyridine was converted into 2-phenylpyridine with phenylithium and by refluxing the dihydropyridine intermediate in toluene for 8 hours. Grignard reagents are not nucleophilic enough to arylate neutral pyridines, only pyridinium salts. Here, ethyl nicotinate was first activated with boron trifluoride etherate and then arylated with a Grignard reagent. Dehydrogenation of the dihydropyridine with tetrachlorobenzoquinone gave a high yield of arylated pyridine. Still less nucleophilic than Grignard reagents are organozinc compounds, but these can be added to pyridines with the aid of nickel complexes. In this example, 5% of a nickel-0 complex was used, and after 20 hours at 130 degrees Celsius, 55% of 2-phenylpyridine resulted. Here, a phenylruthenium complex was generated in situ from phenyl iodide and ruthenium carbonyl. Again, a high temperature and long reaction time were required. Also, organopalladium compounds can add to pyridines, but with another regioselectivity than organonickel or ruthenium complexes. In this example, an aryl palladium intermediate was generated from an aryl triflate, and the main product was a 3-aryl pyridine. This example is similar to the previous one. An aryl bromide was the precursor of the aryl palladium intermediate. Again, a high temperature and long reaction time were necessary, and the main isomer obtained was the 3-aryl pyridine. Here are some further, mostly recent examples, which you can also find in the description of this video. The next presentation of this playlist is about the preparation of pyridines by cycloaddition and rearrangement. These reactions are less relevant than cyclocondensations, but mechanistically intriguing, and some of them give access to pyridines which can be difficult to prepare by other routes. See you then!